Okay, everybody. We've been talking about the applications of neural networks. And in this slide, we see an indirect adaptive control mechanism. Basically, the loop is here, okay? That is, this neural controller receives a command signal and it produces a output, and that output is the input to the plant that is under control, and it produces a response. But the loop is here. The same plant is identified by a emulator, okay? And you compute the difference between the plant response and the emulator response, okay? And that response is fed back through the emulator by taking the partial derivatives to obtain an equivalent error in the control, okay? And there is this feedback loop, okay? And it's the same training algorithm, error backpropagation or Levenberg Marquardt, okay, tunes the parameter of the neural controller so that it produces a better control signal in the next sampling instant. Okay, this is known as the indirect adaptive control mechanism. So it was really very famous once upon a time. Nick's book is here. It is published in 1997. There are a number of figures that discuss different configurations, control configurations of neural network-based mechanisms. I mean, this is known as the indirect learning architecture. Well, we already discussed it. You apply your reference signal to a controller, it produces a control signal, and that signal is applied to the plant, and plant produces a response. So the goal is to obtain y is equal to r, but typically it is not. So you have to perform a corrective action over this neural network controller. So you take this plant output as the input to your neural network controller. By the way, these two guys are identical, okay? You tune the controller here and use it right there, okay? So you take the output as an input to your controller to reproduce the control signal, and this trainer tunes your controller, and you copy the parameters of your controller to this place to obtain a control mechanism. This is also known as the indirect learning architecture, which is based on the inverse of your plant dynamics, okay, which is typically difficult in most applications. That is the closed loop direct inverse control. If you obtained a kind of inverse of your plant dynamics, as shown in here, you get the response of the plant, obtain the output, and your controller uses the error as an input, and the trainer tries to minimize the input of the neural network by changing the control signal. Okay, this is kind of direct inverse control, which is summarized in this book as well. And that is the specialized learning architecture. In the specialized learning architecture, I mean, you know the region where your control signal is, okay? You know the region where your control signal is. Basically, your control signal, without closing the loop, it is difficult to predict priorly where this control signal should be, okay? I mean, is it in between -1 and +1? Is it in between -100 and -50? Or is it in between +50 and +100? So if you don't know that, it becomes a problem to tune or to train the neural network-based controller properly, okay? So if you choose your region incorrectly, then your controller would be the correct controller for an incorrect region, okay? So that is because the specialized learning architecture is proposed. You apply your reference signal, obtain the output of your controller, then that control signal is applied to the plant, you obtain the plant output. Take the difference in between the plant output and the desired signal, obtain the error, and that error is used in training the neural network-based controller. But it is difficult. Why is that difficult? Because this error is the error observed at the output. This error is not the error observed at the output of your controller, and that is because this may be kind of a problematic configuration. And that is the indirect adaptive control. I already shown you in my colorful drawing. You have an identifier, neural network identifier, and a neural network controller. Identifier tries to identify or emulate the plant dynamics, and the error, that is the difference between the plant output and the identifier output, it is here. The error is minimized by this trainer, and the identifier learns plant dynamics. So it becomes possible to take the partial derivative of the output with respect to u by using the identifier. You take the partial derivative of the output with respect to the input of this identifier, and you pass this error back through the identifier to obtain the equivalent control error, which is kind of equivalent, not the exact value, but an approximate value. And if you tune your controller with that error measure, then you'll see that this algorithm works for a class of plant dynamics. Okay, let's say your plant dynamics is given by an affine representation, which is x dot is equal to f of x plus g of x times the control signal. So if you know the functional details embodying the f and g functions, then it will be possible to implement a feedback linearization type of a feedback control structure that cancels out the effects of g and f, and then you would follow the usual well-known loop shaping or feedback linearization algorithms to obtain a nice closed loop response. Well, if you don't know that, it may be a possibility, it may be a method to predict the values of these f and g functions to cancel out the effects of these functions so that your controller provides a nice control signal to your plant dynamics, and your output, plant output, tracks the reference signal correctly. Okay, this is based on a feedback linearization approach. And that is this error, which is called as feedback error learning architecture, FELA. As far as I remember, it was in 1987 by Kawato. Well, there is this usual, feedback loop. And with that feedback loop, you use the reference signal as an input to your controller, which is the feed-forward type of a controller. And the output is added to the control signal that is produced by this usual classical controller. And the classical control output is used as an error measure to tune the parameters of your feed-forward control mechanism. That is a neural network. Okay, it is of course possible to implement this kind of a structure. It is of course possible to download this book and see the details and discussions given for these feedback connections. Okay. Well, typical neural network-based control architecture uses some delayed values of the produced control signal and some delayed values of the reference signal to the controller, and the controller also knows the current error value to produce a good control signal. And this good control signal is also supported by a conventional controller, which could be a PI controller or a PD controller or a PID type of a controller. Of course, it could be an H-infinity controller, or advanced control mechanisms could be used here. Okay, it is a classical controller, and this classical controller provides a nominal, average performance, and the performance is improved by this neural network part. Okay, your plant is here, the produced control signal is applied to your plant, and the response is obtained and is fed back to your control computer. Okay, you take the difference and run the loop. All right. Okay. I know not all of you have some interest to control, and some of you may be working on or choosing thesis from the field of, say, image processing. And neural networks are now very powerful tools in image processing. I mean, deep learning or convolutional neural network stuff, they are able to extract the cognitive content available in an image, okay? But in this course, since this is not a deep learning course, I will not go into the, that deep stuff. It is possible to filter, for example, an image, okay? There is a noisy image, there is a, image which is poorly recorded, and the question is whether we could remove this noisy components from the image. Okay, if we apply this as an input to a neural network based filter, would it be possible to obtain such a clean image? Okay, so how do you filter out the noise from the source? How do we teach what to filter out and how to filter out? Basically, there are several simulation results in my lecture notes. This was the original image, and this is the noisy image, which was an input to my filtering mechanism. And this was the result I obtained. And well, this is a Saturn image. There is a flower, Vinca. With this flower, this is the original image, and that is the noisy image, and the filter image is like the, still there are some noisy components, but it is better than the figures or images you see in the middle. Okay, let me explain how we can do that. Images are composed of pixels, right? And I'm enumerating the neighbors of a pixel. Let's say the pixel is shown by number 5, and its neighbors are 1 in the north, 2 in the west, 4 in the east, and 3 in the south of the pixel you see here. Okay, now I will produce a vector by using the, let's say, RGB values of, or grayscale values of this pixel. Okay, so 1, 2, 3, 4, 5 is here. Okay, this is an input vector now that describes a very narrow adjacency, very narrow neighborhood information to a neural network structure. And here is my neural network, which has, according to this picture, 5 inputs, and which is gonna produce the estimated value of the, let's say, grayscale value of the pixel 5, looking at the values of the neighbors. Okay, so in order to obtain a nonlinear filter, I must train my neural network. In order to obtain a nonlinear filter, I must train my filter neural network. Okay, so you should tell me some noisy images. You should give me some noisy images and clean images. Then I should use that information to train my neural network. Okay, so we will call this is a frame from a noisy image. This is a vectorized form of that frame, and that is the desired value obtained from the noiseless image. Okay, can I do that? Yes, of course. If you tell me an image and a noisy image, I mean clean image and a noisy image, I can train my neural network so that I can develop a filter structure that removes the noisy content as much as possible. I mean, I'm saying that as much as it depends on your neural network structure. It depends your input information. It depends on your, say, neuron activation function, learning algorithm, whatever, okay? It depends on your choices. I will scan the image, all rows and all columns, okay, for each pixel, okay? At every frame, I will reorder the observations or the collected values. You see, for every frame, I will obtain these 5 values, okay? To form an input vector, I will choose the corresponding output from the original image, and this is going to be my training data set, okay? And I will train my neural network to remove the undesired content available in my image. For my results, I trained the neural network for the Saturn image. It was an offline training, and I tested it for the flower, Vinca image, to show this filter is not a specific filter that only removes the noise from the Saturn image, okay? So I should show you that there is no memorization. And my neural network has 5, 10, 1 structures with sigmoid nonlinearity for the hidden neurons, and my output neuron is a linear one. And I used 2,000 training patterns that have been selected randomly. Well, you know, in a small sized image, even in a small sized image, you have thousands of training samples, training patterns. So I downsampled it to 2,000, and that is enough for me. And the training continued for 50 epochs, and the mean squared error for my experiment decreased to this very small number. It is approximately 6, 10 to the minus 4. Okay, this is how it goes. Well, the goal is 0. I mean, the goal is 0, but it does not go to 0. It enters into a this kind of a region, so that makes you wait for a long time. But I stopped at 50 iterations, and I am convinced that my filter is adequately well trained for me. This is the resulting page. You see the original image on the left. That is this noisy image, and my filter structure removes, well, it removes quite a large number of those noisy components, but still there are some points I feel the noisy behavior here. Again, the same happens. If this was my training data, this was my testing data, this is the original image, here is the noisy image, and this one is the filtered image. But by looking at this very simple 5 minutes example, okay, for your 5 minutes, let's say 25 minutes, not 5 minutes, 25 minutes experiment, you'll see that a simple neural network can be used as a filter that removes the undesired content from an image. But you should know that there are very different types of noise signals. As you see in this image, if you apply a higher noise level with this noise level, you see that, well, now from the filtered image, I can see that there is the planet Saturn, but from here, well, the information is, the amount of information when you compare the two figures, this one, the right one is better, of course. Yes, the same happens for the Winca image here. Basically, depending on the noise characteristics, I mean noise variance, noise type, okay, you may be developing different types of image filters, okay. In another train and test, I used 2 hidden layer neural network. First hidden layer has hyperbolic tangent activation function, and the second hidden layer has sigmoid activation functions. Output is a linear one. Well, again, I trained for a Saturn image, tested for the Winca image, and the 2000 patterns. For this time, training continued to 500 epochs, and the mean squared error decreased to this, slightly larger than 10 to the minus 4, okay? And the training noise density is 0.1, test noise density is 0.5. I'm playing with the noise densities, okay? This is how it goes. This is my training optimization page. So you see that there is no need to wait for hours to get a better mean squared error performance. It is satisfactory here, and this is my result. Okay, so this very simple example tells me that I can use a neural network as a two-dimensional filter, okay, as a filter that can remove the undesired content from an image. I mean, I used this example, I tried this example for the leftmost adjacency, for the leftmost neighborhood information, okay? It is of course possible to use 9-input neural network that could use this kind of a adjacency plot or a frame, or 13-input neural network that uses more information. I mean, that is aware of the deeper, say, neighborhoods in a pixel, okay? With this kind of a structure, you are losing 2 rows and 2 columns at the outermost places of a image, okay? So different frames can be considered, but in these cases, you should be aware that, I mean, the computational complexity as the processing time is increasing, okay? Processing time is increasing. So may use other available techniques of image processing, of course, right? So this summary slide tells me the original image on the left-hand side. The second column shows salt and pepper type of noise. And the third column shows Gaussian noise, which has variance 0.1. And the right-hand side, you see the speckle type of noise density. There are different noises, and you may have to develop your own filter, which is peculiar to, which is specific to the given noise observations. Okay. There are other types of applications. I'm closing the image filtering. This one is adaptive noise cancellation. Okay, this one is adaptive noise cancellation. Let's say you are in an aircraft and you are going from Ankara to Istanbul, okay? And the pilot is giving some announcements, okay? Pilot is giving some announcements, but you know that the environment within the aircraft is noisy, okay? There are engines, or there is an engine, okay? And that engine produces some noise, and that noise passes through the physical structure of the aircraft and reaches the microphone of the pilot. When pilot is speaking, this signal C, which is a filtered version of the engine noise, is added to the pilot's voice. And that voice is shown by S plus C, okay? This engine noise is filtered by the physical structure of the aircraft, and the filtered signal is denoted by C, and that C signal reaches the microphone of the pilot. And when pilot speaks, S plus C is processed by the electronic component of the aircraft, okay? The idea here is the following. Is it possible to reconstruct the noise path filter, which is, which is the physical structure of the aircraft? Is it possible to reconstruct or reproduce the noise path filter by a software? And it is this adaptive filter such that this adaptive filter imitates the same behavior of the noise path filter such that it produces C hat, which is very similar to C. Okay. Now my question is the following. I will use an adaptive filter here, and I will remove the response of this adaptive filter from this signal. S plus C minus C hat is the restored signal, and this restored signal will be broadcasted into the aircraft, to the passengers. Okay? The good idea here is that if the adaptive filter, this adaptive filter identifies the noise path filter, okay, then this C is equal to C hat, and I will hear the noiseless pilot voice. Okay, I will hear the noiseless pilot voice. Basically, there is this sinusoidal signal. Original pilot voice is red, reconstructed one is black, and I see that there are fluctuations at the very beginning, okay, at the very beginning, but those fluctuations are, disappearing in time. So this is the noisy pilot voice, okay. This is the reconstructed pilot voice. I see that the pilot voice is getting more and more similar to a sinusoidal. And the norm of the parameter vector, which means that you take the squares of the filter parameters and you add them up and then take the square root of it and show me. If it is convergent, yes, this filter is kind of a reliable filter. You can safely use it. The parameters are not going to infinity. Okay, the parameters are not going to infinity. So this FIR filter, which is a finite impulse response type of a filter, that is composed of an adaptive linear element. It has 25 inputs with a bias term. Okay, so there are 26 adjustable parameters, and I used error back propagation. No momentum, no learning rate adaptation. It's a pure error back propagation. So it is very easy to do this, okay? It is very easy to develop this kind of an application. A simple signal is chosen as the pilot voice, and filter successfully reconstructs the noise and lets us have the pilot's voice as the output. And the training is, well, this is an important point, training is online. Okay, when the pilot, well, there is the pilot voice, it is red. Reconstructed one is black. This is the learning period. It very quickly learns the noise path filter and reconstruct. Well, this is the noisy pilot voice, and the reconstructed pilot voice is shown once again here. This black is equal to this black, okay? And this is the norm of the parameter vector, okay? So let me stop sharing here, and now share sound. Again, share my PowerPoint. Now you should be hearing this voice.
Istanbul.
Did you hear that? Probably yes. This is the noisy one.
Istanbul.
And now I will show you how filtered one works.
Istanbul. Istanbul.
The initial fade out noise is this one, okay? This fades out, and you see the original pilot voice clearly, okay? This is the original.
Istanbul,
This is the filtered,
Istanbul,
okay? And this is the noisy.
Istanbul,
With the final coefficients, you obtain this result.
Istanbul,
The fade out is very quick,
Istanbul,
okay? And you obtain very clearly the noise path filter and remove the noise that comes from the engine as shown here, okay? This adaptive filter identifies the noise path filter. It learns how it produces, since the inputs are the same. So if they are identical, then they will produce the same output. So S, here S plus C, S plus C minus C hat, this C minus C hat is very close to 0. So you clearly hear the pilot voice. This is a nice application of adaptive noise cancellation. It is based on the identification of the noise path filter correctly. Okay, this is a digital filter, and this is another digital filter, which is adaptive and a finite impulse response type of a filter, as shown here. And it has 25 inputs. I mean, those 25 inputs are the signal and its delayed value, delayed value, delayed value. You take 24 different delayed values, the successive delayed values, and the 25th one is the current one. 26th one is the bias term, and you tune those 26 parameters and obtain this online filtered pilot voice.
Istanbul,
It should be, I mean, convincing for you. Okay. I will not explain you the very large scale integration. VLSI is an electronics technology. So I will not go into the fabrication or production or design details of these stuff, but we started with a biological reality, and we obtained a mathematical modeling, and then we obtained, people, let's say, obtained physical chip-wise implementation of neural networks, okay? Very recently, one of my friends from Top University designed a superconductor-based neural network structure. So it is possible to obtain electronic hardware and pack them to obtain chips, okay? The key actions within this kind of a chip are the multiplication, summation, and thresholding. Some of you are from electrical engineering, and the other guys are taking the introduction to electrical engineering, circuit analysis like stuff. So there are two operational amplifiers here. One of them is for the nonlinear activation, this parenthesis, okay? This operational amplifier produces plus 12 volts or minus 12 volts if you are supplying it with 12 volts, okay? Plus VCC or minus VCC. So this is the threshold. There is a voltage source. So if this output is above this theta, then this is plus VCC. If this output is below this theta, then it is equal to tau is equal to minus VCC. So what is this tau prime? This tau prime, it's a very simple electronic circuit. Tau prime over R plus U1 over R1 plus U2 over R2 plus dot 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 UN over Rn is equal to 0. So this is a simple, node equation, Kirchhoff current law equation. So it is possible to write this. It is equal to 0. You solve for tau prime, and then you implement your neural network. This is a simple, very simple hard nonlinear activation function type of a neuron. Okay, it is possible to implement this. So in VLSI, there are many different techniques that you can use the classical, components of electronic circuits, like, current mirrors you see here. There are, well, some standard structures you see here. There are current mirrors here. Okay, so it is possible to implement this. Figure is taken from this paper, which was 20 years ago from a conference that I joined also in Washington, D.C. And it is possible to obtain neural network structures with this kind of a activation functions that are all tunable, that are all realizable. Okay, so in digital domain, it is possible to obtain more versatile neural networks. In those cases, the size, chip area, power consumption, operating speed are important parameters, and I have seen many master's theses that consider power consumption or chip size or whatever. Okay, so training is a difficult part of this business. Training on chip or the chip in the loop are the strategies. The part non-idealities are difficulties. Operating speed is important parameter, and quantization errors for digital neural networks are important parameters. Okay, so I will stop here